what are the sorts of, we're just really scratching the surface of the questions that we're trying to ask in terms of how we can think more formally about design. So I'll start off by saying that this is not just my group, this is not just my work, it's the work of my group. And so a lot of my PhD students have been working on these sorts of ideas, as well as a lot of collaborators that we've been working with. I've highlighted in green here the ones whose work I'll primarily be talking about today. And just wanted to acknowledge them before I share their work with you. So normally, when I start talking about robot design, I go back to this idea of, well, you know, when I was doing my PhD at MIT, we had this dream of, well, let's say in the future, we want to have this ability to create a custom robot. And you don't need to be necessarily a robotics engineer, but maybe you have this idea of a robot that you want to create. In this case, this person has an idea of maybe some kind of insect-like robot that they want to move over this kind of rocky terrain. Well, wouldn't it be nice if, rather than having every PhD student here spend N years working on designing this robot, we were able to create computational tools that allow these people to help these people to input robot specs, help them to make design decisions, really streamline the design process so that they can very quickly then take their design, fabricate it in real life, and then use it in whatever environment it was that they were thinking of, right? And so the key is really, well, what is it that goes into this system? And originally, when we were trying to formulate these problems, we were saying, well, let's really try to specify what is a robot, what is a task, right? And so we came up with this kind of way of describing these systems, which is, well, a robot, it has some geometry, it has some joints, it has degrees of freedom, it has some controllers associated, right? These are all variables, design parameters that are associated with this robot. There's also this task that we want the robot to accomplish, right? There's an environment that we care about. That environment has geometry, but it also has physics associated with it. We care about particular contact modes potentially. And then there's some objective, some performance that we want to achieve. And if we can write all of this down, then, well, the problem of design is easy, right? The problem is, well, we want to be able to achieve this objective over the space of robots subject to some constraints, right? And then if we can solve this problem, we're done, right? So how do we solve this problem, right? And so during my PhD, we were thinking, well, maybe one of the ways that we can try to approach this problem is through modularity, right? Let's say, well, there are these different robot components that we care about. Maybe we can create modules for each of these components and figure out when can we connect them together? How do we then simulate the robot in order to get it to achieve particular tasks? And we said, well, this part here is really hard. This task specification is really hard. So let's focus just on legged locomotion. So we built this system here. We called it Build-A-Bot. This is a modular design system where, you know, you take these components here, which we hand designed, and now you put them into this 3D workspace. A user can come in and change the shape. These shapes are all parameterized, so we can keep track of their geometry, kinematic constraints, all of that. Users can drag in other parts and connect these parts together. And as they do that, we imposed a grammar on this system that said, well, if you're connecting particular types of parts together, then that implies that you're connecting them with joints or you're connecting them with motors, and there are certain controllers or kinematics that are associated with these structures. And so in order to make sure that this robot satisfies fabrication constraints, well, we need to keep track of the geometry and also what the fabrication plan is going to be. And then if we also want the robot to be able to achieve some particular task, in this case we said, well, just get the robot to walk over this ground. Then we can simulate the robot executing the particular gate associated with our grammar, right? So in this case, very constrained. And then tell the user what is going to happen. So in this case, they're attaching the different parts of the robot together, and then you'll see in a minute the robot being simulated. But basically, if we can modularize this design process, then we can very quickly provide the person with feedback as to how their robot's going to perform and allow them to make these design changes while making certain guarantees on geometric feasibility or the fact that this robot can be fabricated, right? And so this software, we said, well, it gives us the first step, right? And so we can take these robots, we've shown that they can be fabricated, but let's see what other people do with this software. So what we did was, a couple years ago, we took this software and we brought it to ICRA, which was very conveniently held in Philadelphia at the time. And so we put a booth out, said, well, everybody, why don't you try to design a robot that's going to go over this environment? We'll give you a score, which is, well, how fast you can cross this finish line, and we'll see what people do, right? And we wanted to track how people actually approach the design process when they're given a task like this in a system that looks like this. So this, we ran this study with about 37 people. 37 people participated, ranging from undergraduates to professors to people in industry, basically the people that we could bother in the exhibition hall to interact with our software. And we tracked all of the different operations that they took in the software to see how they approached this design process. And so what you're seeing on the right here is what they did over time. And we looked at, well, what time are they spending in the design phase? What time are they spending in the gate design phase? How much time are they spending actually testing the robot? And observed the sorts of things that they were doing. And then afterwards also talk to them to say, well, what was your thought process as you were going through this design process? And so this here is an example of the sorts of actions that one particular user took during the study. And I think there are a couple of observations that I wanted to make, which is, well, we tracked their score over time to see how well the robot was doing. The max score that was achieved during the study was around like 1620, I think. So this person ended up achieving something pretty close to the best score, but started out with a design that was not actually that great. But one really interesting thing that we discovered, together with Christina Wilson, who works in psychology at Oregon State, is that people really seem to get into, they really seem to zoom in on a particular design very quickly, right? And so if we look in particular at these lines here, we have the part added, how many times they modified the existing design, and how many times they deleted parts in the design, which we think means that they were changing their mind about what was going on, right? And so there's a lot of parts being added at the beginning, right when they're starting with a new design. They did one test where they got kind of medium performance, right? And then this part here, not so much happening on the morphology of the robot itself, but a lot of tuning happening on the exact geometry, right? And so this was pretty typical for a lot of the users that were in the study. And what we concluded was that, people go into these design problems, and, well, what they're doing is not really solving the optimization problem that I showed before. They're not saying, well, what is the best possible robot? Let me look at all the entire design space, really think about all of the robot parameters I can deal with, and then find the best design that's going to give me my functionality. But rather, they really find something that they think is going to work, right? And then they kind of iterate over that particular design, right? And I think those of you who are designers, and even me myself, that's kind of the mode that we use for design, right? And so after seeing this, we kind of took a step back and said, well, what is it then that we're actually trying to achieve with these sorts of design approaches? Because at the beginning, when we started on this study, Christina had done a lot of reading in the literature and said, well, actually, what we've seen is that there's a difference between novice and expert behavior, and novices tend to, have design biases, and experts tend to be more willing to explore the design space. And we did not see that here. We saw really everybody just zoom in on a particular design and iterate on it. And what we thought was, well, maybe then what we're trying to do with these design systems, or when we design robots, is not actually come up with the optimal design. A lot of people are really just trying to get a design that works, right? And so this is related to some of the ideas that people have been throwing out in the mechanical engineering design community for a while, which is, well, what is the difference between how we think about mechanical design or robot design or design in physical spaces, and how we think about things that are very modular, like VLSI, or how we think about computer programs, right, which are also very modular. And I really like this sequence of papers, one from 1996 and the following one 1 year after, 1997, where the first one is this title. It says, "Why Mechanical Design Cannot Be Like VLSI." And the argument here was, well, mechanical design is really, really hard. The reason it's really hard is because actually mechanical design is inherently not modularizable in the way that VLSI and computer programming is. Because you have all of these mechanical components that are interacting with each other, and when you change one part, that affects the behavior of another part. And so inherently, we cannot actually deal with mechanical design in the same way that we deal with electronics, and so you kind of have to design the whole system altogether. 1 year later, there was this paper here from Eric Entenson, which was called "The Potential for Mechanical Design Compilation," which is basically the complete opposite viewpoint, right? And this paper was actually written in response to the first one, where they said, well, you know, there are things in mechanical design that are very interconnected, very interrelated, and so when you change one part, you do inherently affect other parts. But there are also some things in mechanical design that are modularizable. And maybe the key to thinking about mechanical design, or in my area of interest, which is robot design, is figuring out what parts of that design space can be modularized. And there's another part way at the end of the paper, which is also that maybe also the key to allowing us to use modularity for these sorts of design approaches is to accept that sometimes when we take these compilation or these modular approaches, that the design that comes out is not going to be optimal, right? And so as long as we can achieve particular functionality out of the design itself, and we can achieve something that's possible, well, maybe we're willing to make sacrifices on the other part for the ease of the design process. So this has really been an inspiration for the way that we've been approaching design and computational design for robotics in our lab. This idea that, well, if we want to make design more accessible and we want to make it easier to achieve, actually what we need to do is not necessarily try to solve these really big optimization problems, but rather think about how do we simplify the design process and look at interactions between components in a way that allows us to first just figure out what designs are possible, right? And then second, then take those ideas and then figure out what designs are practical, not necessarily optimal, right? So that kind of sets the stage for the projects that I want to talk about today, and really sets the stage for the title of the talk that I proposed, which was trying to link design approaches to planning problems, where people have really been thinking about these ideas. Well, what is optimal versus what is practical when it comes to how we get robots to plan our own space. Now we can also think about how we do this in the design space. So I'm going to start then with a project that we started thinking about a couple, I guess 3 years ago now, where we said, well, let's start with a very particular type of robot. Let's start with manipulator arms. And let's not even think yet about actuation. Let's just think about kinematics. And let's think about, well, if I want to create an arbitrary manipulator arm, serial manipulator arm, when is it possible for me to actually construct this arm? At the time, we had a very specific focus on origami-inspired design, but I'll show you later that actually the algorithm we came up with isn't necessarily restricted to origami. But what we said was, well, all I want to do is make sure that if I have a robotic arm, I have a particular kinematic structure I care about, I want to be able to fabricate that arm. What is it that I need to do in order to achieve this particular kinematic specification? And so in order to do that, well, we said, well, the way that we're going to specify these kinematic arms, now the task specification is very clear. We're going to use the Navier-Hardenberg specification, which is probably the most popular way of specifying robotic arms, right? So how many people here are already familiar with the Navier-Hardenberg? Okay, some people. So the idea behind Navier-Hardenberg is that, well, actually what I care about is not the full structure of the robot, but what I care about is these axes of motion. So this is a drawing of a 3-link manipulator arm with 3 revolute joints. So the cylinders are revolute joints. And the axis of motion is down the center of the cylinder. And if I want to describe the kinematics of this arm, I don't actually care where the joints themselves are, but I do care where the axis of motion is. And the axis of motion can be described by 4 parameters. So the 4 parameters tell me where the direction of this axis of motion and the location of that axis of motion relative to the previous frame, right? And so this allows me to describe the kinematics of this structure. And if you want more detail than that, then Navitt and Hardenberg have a really great paper describing what it exactly goes into this specification. But what's interesting here is that basically this specification tells me exactly where I want the axis of motion to lie, but I don't care where the joints are, which gives me an extra design degree of freedom, right? So if I can place the joints really anywhere I want, that allows me to make this robot fabricable as long as the axes of motion are correct, right? And so we said, well, how do we go about then designing structures that are physically realizable, that achieve these kinematic specifications? And before I tell you the solution to this problem, or our solution to this problem, I'm going to take a sidetrack. So the sidetrack that I'm going to take is on path planning under curvature constraints. So many of you have probably heard of Dubin's path planning, or planning for cars or airplanes, right? These are vehicles that have been studied for a really long time in robotics research that can only follow paths with some minimum curvature, right? So if I want this car to go from this position, this orientation, to that position, that orientation, I can't take a straight line path. I need to follow a path that consists of curves, straight lines, and then additional curves, right? And back in the 1950s, Dubin showed that in 2D, these kind of curved, straight, curved paths are shortest length paths for these sorts of planning problems. And in the 1980s, I believe, then Hector Sussman showed that in 3D, then these paths can also be used to describe these sorts of the sorts of paths you would take from starting positions and orientations to ending orientations and positions in 3D space. Now, what's really interesting about these paths is that actually these are paths that robots can follow in 3D space, but they're also paths through 3D space that basically create rigid transformations, right? So if I have a frame down here and I have a frame up there, and I create a series of physical objects that implements these turning and straight line paths, then what I get is not a path that a robot needs to follow in 3D space, but actually a physical link that generates a rigid transformation that I can use to create a particular relative orientation and translation between my starting and ending frame, right? And so we thought that this could actually be a way for us to approach the problem of design of manipulator arms, because what this means is that if we put a joint down here and a joint up there, as long as we can calculate and then create this path, then we have an arm that's fabricable, right? So what my student did, Wei-Shi Chen, was he designed, in this case, origami modules that implemented these different paths. So we have this module here, which gives you curved path rotation, this module here, which gives you straight line motion, and then additionally other modules that give you joint rotation and joint translation. And the key now then to designing a manipulator arm is actually mapping this design problem onto a Dubin's path planning problem. And as long as we can solve the path planning problem and we can combine these origami modules together to create those paths, then now we have a valid arm. So the key insight to doing this then is that actually when we choose a particular kinematic specification and we want, in this case, the Navitt-Hardenberg specification, which only gives us the axes of motion, the joint locations themselves are not necessarily fixed. right? And normally, when we're trying to design robotic arms as mechanical engineers, you try to take the joints and put them as close as possible to wherever the other joints are so that we don't have any of this like extra mass or volume around. But in this case right now, I'm going to say we don't care, okay? So if I have my arm, for example, and my elbow here has the axis of motion down this line, actually, for the purposes of figuring out where my hand is going to be, my end effector is going to be, it doesn't matter if my elbow is right here or if it's over here, as long as the axis of motion is correct, right? And so I can use that extra degree of freedom in order to be able to design these sorts of manipulated arms that satisfy my kinematic specification. The reason I can do that is because I can now pull from existing properties that have been discovered for Dubin's path planning, that these paths can be calculated as long as my joints are sufficiently far apart, right? And so what I need to do now is basically go through this process of figuring out for every joint that I want to connect together, where should I place it on its axis of motion in order to bring it, into a location where I can actually route these paths. Then I can convert those paths into these physical structures, and then I can do that iteratively over the entire structure of the robot, right? And so here, what you're seeing is the process of designing a spherical joint. So what we have is these three joints here, which have axes of motion that all coincide here in the middle. That was the diagram that you saw at the beginning of the video. And then these are the paths that get automatically generated through this process of converting this problem into a Dubin's path planning problem. Each of the segments of this path here get converted into the equivalent origami pattern, which in this case is a tubular pattern. So it can be either constructed through folding, or if you want to print out 3D tubes on a 3D printer, you can do that too. But what happens is if we take this pattern and then we fold it, then we get a physical structure that lies along this path. And you can see the revolute joints in these three locations. If we draw where their axes of motions intersect, it'll be right at the center of this mechanism. So this here has the exact same kinematics as a spherical joint. Not to say that this is necessarily yet a spherical joint that you would want to use, but what we've shown is that it is possible to take these sorts of kinematic specifications and automatically generate some version of a fabricable structure that would have the correct specification. So this process here actually works for pretty much any dynamic Hardenberg specification for serial chains. And we've implemented these ideas, all of the modules, into a GitHub repo. If you're interested in designing your own manipulator arms or spherical joints or whatever it is you care about, you can download this code and input your own dynamic Hardenberg specification and see what comes out. So in this case, we basically said we just want a kinematic specification to a fabricable plan. What are we going to do with this result? Well, now that's the second question, right? How do we actually think about then when these sorts of designs are practical? And so we decided that, well, this sort of idea, maybe we'll try to use it in order to design a quadrupedal robot. Sounds fun, right? So what we decided to do was say, well, we want to design a quadrupedal robot. We wanted to have 8 joints throughout the entire body. In this case, this is not a serial mechanism, right? This is a robot with 4 parallel legs. But actually, you can break it down into 2 serial mechanisms by cutting the robot in half, right? And so the way that you can then take the tree associated with the robot and decompose it into chains is we can find longest chains throughout this graph, right? And so now what I need to do then is if I want to design a fabricable version of this robot, I need to design the kinematic chain associated with the body. And then I also need to figure out all of the actuation, control, everything else associated with it, right? So this part here, presumably, is now relatively complete, right? I need to figure out where the joints are that I care about, and then I need to design this fabrication plan. The key now is how do I make this whole structure more compact in order to make this robot not really unstable, but still allow me to input all of my actuators, right? And so the way then that we start thinking about this problem is we can still build on the insights from designing arbitrary kinematic chains I showed you before, but now we also need to take our actuation into account. Our actuation affects two things. It affects the volume of space that this actuator is going to take up, and actually the joint location affects how much torque it is that the motor is going to need to produce, which then affects its volume, right? So the volumetric constraint is not too bad. Actually, since we were already treating this problem as a path planning problem, what we need to do is route these links through 3D space while avoiding whatever space the motors take up as if they were obstacles, right? And so these sorts of paths can now be generated that allow us to place these motors. At the same time, the torque requirement imposes length constraints. And so now what you can also do is, instead of arbitrarily placing these joints in 3D space in such a way that these paths can be routed, we can add an optimization on top of that that allows us to make everything as compact as possible while satisfying all of the constraints associated with routing Dubin's paths, right? So if we do that, then we get a chain that looks like this. This chain here has the kinematics that we care about for the robot that we're trying to build, but it also has space in there for us to mount all of the actuators that we've spec'd out to produce this robot. So what you're seeing now here is the resulting quadrupedal design. This is a body that has been folded by hand by Wei Shi. The body of this robot, though, has been designed through this algorithm that I showed you previously, where he basically specified exactly where he wanted all of the joint axes of motion to go, and then folded this and then put all of the motors on. This is the robot walking, and then what you're seeing here is us also trying some more dynamical gates, the robot bounding, or in this case, bounding. And being able to withstand the forces and torques associated with creating these maneuvers. I will say that this is actually the fourth iteration of this robot that you're seeing here. The first iteration that we designed, we actually forgot to leave room for all of the motors that we would need to put on top. And so when Wei Shi tried to mount all of the motors and electronics, none of them fit. There were huge collisions. It didn't work. But then we were able to add in all of the extra additional constraints associated with routing these paths around the motor volumes. And what you're seeing here is the result. So these robots here, then we've been able to take advantage of our algorithms for generating these bodies to iterate over the design within a few days at a time. So between the first version, which couldn't take any motors on it at all, to the second version was about 3 days. And then after that, every time we run the robot, we notice an issue, oftentimes material fatigue, then we can iterate over the design within another few days to a week. So, so this now allows us to think about these sorts of kinematic designs without really thinking about the fabrication specifications other than the material. So to compare this robot then to existing quadrupeds, this one here on the right is the mini cheetah. The one on the left is ours. We call it the dynamic origami quadruped, or DOQ for short. The mass is much lower because in our case we're building everything out of thin shells. And the degrees of freedom are also lower because we decided we didn't want to go for the full 12 at the beginning. But in terms of size and capabilities that we have, they are pretty similar to existing quadrupeds that other people have built. So, any questions so far? Oh, yes.
I guess just curious, how did you incorporate all of the force and torque constraints into the kinematic specification to make sure it doesn't collapse under its own weight?
Sure. So the force and torque constraints, which I really glossed over here, I guess there are two different types that we need to think about mainly. One of them is the actuation torque, right? And then the other one is forces on the robot body that will affect its ability to withstand the weight of all of the other components. So for the second one, I'll talk about that in a minute. In this case, we just assumed that all of our rigid tubes were actually rigid. For the actuation torques, basically what you can do is take a look at families of motors, and there are scaling laws associated with families of motors. And so if you know what the torques are associated with moving particular components of your robot because you know what the mass distribution is, then you can take those resulting torques and then use them to figure out the size of the motor relative to whatever your initial specification was. And then we use that to then design the kinematic structure. Yeah. So, but the question about structure then becomes really interesting because one of the other things that our lab cares about is compliance. And you might notice that on this table here, I did not say anything about cost of transport or energy consumption, or how much work these motors were actually doing. In our case, because this robot is very, very floppy, because these rigid components were not actually rigid, we wasted a lot of energy. The cost of transport here is probably about 10 times what you might find on a commercial platform. And so from there, we really started to think about, well, how do we then start design with the compliance of the structure in mind? How do we think about the extra flexible degrees of freedom that might be in this robot, and how do we tune them to give us the sorts of deformation that we care about? So for this problem, we went back again to manipulator arms. And we started thinking about, well, if we have say now a tubular structure that is actually compliant, it's not rigid the way we were assuming before, how is this structure going to deform? And the way that we started to think about modeling these structures was as networks of springs, right? This is kind of a generic model that you could use for our origami robots, but also for many of the soft robots that exist in the literature right now. And if we think about these springs then tuning the stiffness of these springs gives us different deformation modes for this robot, right? So what you're seeing on the right here is a version of this 3-segment platform that we built, where actually the stiffness distribution throughout this structure is not uniform. So if I take a tendon and I pull down the center of this platform, the softer springs are going to compress first, right? And then the stiffer springs are going to compress. And the way that the structure deforms is going to depend on the stiffness distribution. This is a really abstract version of what was happening on the legged robot that I showed you on the previous slide, where actually in that case the stiffness is dictated by the particular geometry of the fold patterns that we care about, right? But we start with this particular abstraction because it allows us to think about the structure in a little bit easier way. So the way that this structure then deforms depends on the energy landscape, right? So if I'm pulling the string this slowly, then this whole structure is going to tend to bend in the direction that brings it to a state of lowest energy. And what we did was that for these particular types of tubular structures, we can construct stiffness matrices associated with them, but those stiffness matrices have a particular structure in them, right? And so actually for structures like this, the tubular structures that we've been designing, the way that these robots deform has an analytical solution. And so we can construct these matrices associated with kV. These are the stiffnesses at each of the springs. Here we have theta V. V is basically the ID associated with springs along the circumference of this structure. And V is the number of springs around the circumference of this structure. And then the way that this structure then deforms is dictated by basically this matrix equation. So what that means is that actually if I have this sort of solution, then I can use it in order to figure out which direction the structure is going to deform when the stiffness changes, right? I can find energy gradients in this energy landscape, and I can manipulate those gradients in order to get the structure to tend to a particular new pose. So what we found is that what we can do is use gradient descent-based approaches very similar to potential fields and potential field planning approaches, right? Where basically we're getting these structures to move along these energy landscapes and tune the local minima of these energy landscapes so that the deformation is the one that we care about. What we do here is not change the lengths of tendons or DC or actuate DC motors the way you might normally think of in traditional rigid robotics. But what we're thinking now about here now is stiffness change, right? And so these correspond to material properties that are associated with the springs throughout the structure of the robot. So if I take this idea and I say, well, what I'm going to do is now assume each of my springs is an actuator, right? And let's say that I want this manipulator now to bend in a particular way. I want it to be, for this particular scenario, I want it to be such that when I pull a tendon down the middle, the whole structure is going to deform and the robot is naturally going to get its end effector to this purple triangle. I can do that by manipulating the stiffnesses of these springs. So what you're seeing here in this animation is each of the thicknesses of these springs here corresponds to its stiffness. This robot here is basically just following gradient descent along in order to update those stiffnesses and get this robot to deform into the right shape. Once this happens, I can now take this stiffness distribution and use it as part of my design if this is the particular deformation that I care about, right? What's really interesting is that if I'm modeling these soft robots in this way, then I have a lot of extra degrees of freedom, actually, right? And so this robot here, I can get the whole structure to deform so that it curves and the end effector hits this purple triangle. But I can also then uniformly scale all of the stiffnesses so that I can achieve these configurations with greater stiffness or greater softness, right? And so actually, since the system is now over-actuated, I can use these extra degrees of freedom to tune the stable configuration and the strength of the robot at the same time. So these sorts of ideas, I think, really highlight the way that our lab is now headed, which is to think about how these sorts of design problems can be cast as also these planning problems. And I can take these sorts of ideas where I say, I want these robots to follow gradient descent in stiffness and implement them either in real time, which is what you're seeing here, where we designed these electromechanical actuators to be able to tune stiffness on the fly. Or we can take the results of these sorts of approaches and then implement them onto fabricated systems. What you're seeing there is the same system, but without the motors. And so that one, you change the stiffness and then it deforms in a particular way, in this case, an S-shaped curve. So those are the sorts of ideas that we're now starting to think about in terms of how do we think about these extra properties of the robot, these sorts of material stiffnesses, as an example, and treat them as actuators, potentially, or actuatable degrees of freedom that now allow us to take advantage of existing approaches to do design, or if in the future we manage to get these tunable stiffness actuators to be smaller and more compact, or for planning. Okay. So in this case, I talked about material stiffness, but I wanted to take these last few minutes, I believe, yes, to give you a preview of where we're taking this work in the future beyond just body robot design. So these sorts of ideas work not just for soft robots, but we've started to learn that they allow us to start thinking about how robots also move on compliant surfaces, or how we think about the compliance in the robot combined with the compliance of the environment. So what you're seeing here is videos not from me. These are videos from Fei-Fei Chen at USC and Doug Gerelmak at UPenn of a quadrupedal system, commercial quadrupedal system, using its gait that it comes with to try to walk on a sandy environment. What happens here is that the sand is very compliant. You're seeing it's kicking up sand every time it walks. Depending on how much compaction the sand has, the robot is feeling different forces coming from the ground. And when it gets to a particular type of ground, it can't handle it, right? The way that the ground deforms makes the robot go unstable, and it flips over, right? At the same time, these folks have found out that actually you can use signals from the motors in these robots in order to detect ground forces as the robot is walking. So what you're seeing here is another video from Feifei's group where she's just having this robot now walk in white sands. And as it's walking, it's recording the currents coming in at the motors and converting those currents into forces. At the same time, this robot is tracking the positions of all of its joints, so it can also figure out how much the toe is intruding into the ground. And what you get are force displacement curves for the robot's foot into the ground that look like this. And so actually these sand-like environments, they look a lot like springs, right? And so once, so Feifei and I were talking and we said, well, actually, this is a really interesting way to then think about robot interactions with compliant grounds if the compliants are very spring-like. And the way that we can model these sorts of robots look very similar to the segmented manipulator arms that I showed you before. In this case, now we have a rigid body that is the robot's body itself, legs, which you can control to act like springs through pre-ID controllers, right? And springs which represent the actual ground, right? And so we can try to figure out how to tune these material properties, right, in order to get the robot to be able to walk stably over these sorts of surfaces. So this was the start of a new project we recently started in November that we're very excited about. This is a project that is part of NASA's Luster program that we lovingly call trusses. It stands for Temporarily Robots Unite to Surmount Sandy Entrapments, Then Separate. The premise behind this idea is that robots now can take advantage of their sensing to detect interactions with the ground. In order to do that, or when they do that, they get a sense of these ground properties and they get a sense of how compact the ground is, and what will happen when they try to execute particular walking maneuvers on this ground. And then based on that information, we can design configurations for robots that allow them to navigate over these environments more reliably. So the underlying hardware behind the systems that we're going to be working with is the spiral zipper and the variable topology truss that Mark Yim is working on at UPenn. And the idea is that then we can take these trusses and we can connect robots together in order to create these sorts of networks where the robots don't necessarily just have the interactions between their legs and the ground, but they can also apply forces to each other to create lateral motion if they need to resist particular types of instabilities. So the idea is then we can take all of this work that we've been thinking about on the material property side and the physical design side, and now use them to also come back and do more interesting planning. So I'm running out of time, so I'll just show this video real quick, which is that this is basically the newest version of the controller that I showed you before for a manipulator arm, but now is a robot here with 4 legs. What you're seeing here are reaction forces from the ground and trusses connected to it that are trying to move it around in this environment. We'll see whether it plays. Okay, so the idea is that let's say another robot is connected on this side. How do we move this robot around using these truss changes, but also changes in the leg interactions down here? And we can move these robots over these sandy environments, these spring-like environments, by using very similar controllers to what I showed you for the soft arm. So looking forward, I think this project really is really exciting to us because it really allows us to think about the interaction between the design of the robot and the planner. What we're looking at in the future is then how we think about reaction forces that are compatible with the other robots that are actually doing this manipulation, directions of motion that allow these group to move in towards terrain that is more safe to them, how we think about the connectivity of the truss now, because all up until now, I've specified a particular network that we're analyzing, but now we have the ability to design the network to produce the sorts of forces that we actually care about. And we can all simultaneously think about how these robots get into the right configuration to actually connect in these ways. All of these problems here are planning problems that focus on what design affordances there are and what degrees of freedom there are and how we can manipulate those degrees of freedom in order to get more capable systems. So as a last note, I'll say that if these are the sorts of things that you're excited about or that you think are interesting, in 3 days, if you're going to ICRA, we are holding a workshop on co-design in robotics where we're trying to think about the interaction between the robot body and the planner. And the questions that we're really thinking about are, what are the particular challenges that we need to deal with over the next few years as we're thinking about these sorts of problems where robot body and robot behavior are tightly intertwined? And are there new areas of research or methods that can really help us to tackle these problems in the future? So I invite you all to come to the workshop if those sorts of things are interesting to you. And with that, I'm happy to answer any questions. I think we're running late as well. Yes.
In the last part of the presentation, we talked about compliance of the environment for robots.
Yeah.
So the environment, compliance, and flexibility can change over different reasons.
Yeah.
So how would you optimize your robot for all the different?
Yes. So there are a couple of approaches that you can take, right? So one is we can only deal with environments in this case that we've sensed before, right? So we know something about the ground properties based on the way that the robot has either just encountered the ground or it has a map from its previous interaction. If we have that information, then the stiffness of the ground is, let me deal with one case first, which is that the stiffness of the ground is not changeable, right? And then what we're doing is manipulating the stiffness of the robot through its PID control or whatever other force control that we put on the robot to change its interaction with the ground so that it can modify the full stiffness, right? Another mode that you can think about, though, is that if the robot knows something about how the ground properties affect the stiffness of the ground, then you can actually have the robot there and intentionally stamp on the ground or fluff up the ground in order to change its properties, right? And now you can potentially get better navigation for future robots going through that. Yes?
This may be more of a hypothetical question, but towards your direction of compliance in mechanisms and between modular components, have you also explored variable damping between components for controlling the dynamics as well?
Yeah, so that is not an area we have actively explored, mostly because we don't know how to verify any of that physically. But I know there are a lot of people who are working on active damping actuators and materials, and I think if we got to the point where we could feasibly think about experimentally verifying those sorts of ideas ourselves or with them, then we would look at it. All right, great. I think that's it. Thank you.